We're trying to explain how block ciphers work. We've mentioned the concept, which I think most people understand, that this cipher needs to be reversible. That's first point. That is, if a cipher is irreversible, then we cannot decrypt. If I encrypt using this information, then if I encrypt 10, I get ciphertext 01. If I send you the ciphertext 01, you try to decrypt, you won't know what plaintext I had at the start, because 01 maps to either 10 or 11.
So reverse mapping in terms of mathematics is one-to-one function only.
Yes. We cannot have a one-to-many mapping here. So that's the one requirement. That is, it needs to be reversible. If we have an n-bit block cipher, we take n bits of plaintext as in and produce n bits of ciphertext as out. The example that we have as a 2-bit block cipher, n equal to 2, then there are 2 to the power of 2 or 4 possible input plaintext values. With 2 bits, we've got 4 possible plaintext values. They are the possible inputs. If we do not allow irreversible mappings, that is, we just have reversible mappings with a 2-bit block cipher, then one possible mapping from the input plaintext to the output ciphertext is shown in this column here. That is, 00 maps to 00, 01 to 01, 10 to 10, 11 to 11. It's not a very useful mapping, but it's possible. It's reversible. That's okay. Another one is shown in this column here. I could map the plaintext values to these 4 values to get ciphertext. The only difference is I rearrange these 2. And a third. And in fact, the total number of possible mappings from these 4 plaintext values to a set of 4 ciphertext values with a 2-bit input plaintext is 24. It's the total number of arrangements that we can have of these 4 values. If we arrange 00, 01, 10, 11 in any order, then we'll get 24 possible arrangements, which is 2 to the power of 2 factorial. 2 to the power of 2 is 4 factorial. 4 factorial is 4 times 3 times 2, which is 24. In general, we get 2 to the power of n factorial possible arrangements or possible mappings from some plaintext to ciphertext, or also called transformations. Same thing here, mapping or a transformation. So that's the maximum possible reversible mappings we can have with an n-bit cipher. What is the key in this case? The key is the information that tells us which of these mappings to use. I choose one of these 24 mappings to use. That is, I'm going to encrypt some plaintext, and I choose one of the 24. Let's say I choose mapping 3 here. That means when I take plaintext that I want to encrypt, let's say the value 10 is the plaintext I want to encrypt. If I've chosen mapping 3, then the ciphertext will be 00 as output. And I will send the ciphertext to you. You need to know that mapping that I used to decrypt. There are 24 possible mappings. You need to know the one I used in order to decrypt the ciphertext. You need to know that I used mapping 3. That, in effect, the mapping that we used is the key here. If someone else knows I used mapping 3, then they can decrypt the information. So the mapping selected is the key. We have 24 possible ciphertext values. We have 24 possible key values in this case, the number of possible keys. Or in general, 2 to the power of n factorial possible keys, if we generalize to n bits. How do we, let's say I choose mapping 3, and I need to inform you somehow that I've chosen mapping 3. What do I tell you so that you can decrypt? I can say I chose mapping 3, but how do you know that mapping 3 is this one and I didn't do it in some other order? So the basic way for me to tell you which mapping I chose out of these 24 is to send you, at some other point, to send you the key where the key composes of these 8 bits. And let's assume that if I send you these 8 bits, so I'll just use a comma to separate the 4 different pairs. Mapping 3 was 0, 0. That's a key in this case, because with that information, under the assumption that the ordering is that the plain text, the first plain text is 0, 0, and then 0, 1, 1, 0, 1, 1. That is, it's in numerical order. Under that assumption, if I send you this, you know that I'm using this specific mapping to encrypt. So in fact, the key is this set of 4 or 8 bits, these 4 values here. If I choose a different mapping, maybe mapping number 24, then for me to communicate that to you, then I would have to send you these 8 bits, the 4 values. And the number of bits here is n, that is 2 bits, and there's 4 values, which is 2 to the power of n. That is the length of the key in general in our example is 8 bits, but in general is n times 2 to the power of n bits. So in general, using this approach, then we have a key which is n times 2 to the power of n bits in length. There are ways to, well, you can think of approaches to try and reduce that and to send this information in some equation form, but it turns out it doesn't work. There are weaknesses in that as well. We'll see why that's important in a moment. One way to implement this mapping is to say that, okay, we have when we do the encryption, we have 2 bits as input. I want to encrypt the value 1, 0. I'm using the 3rd mapping. I have 2 bits of input, and I map that to one of the 4 possible states. In my case, I would say it's state 3. The bits 1, 0. If this is state 0, 1, 2, 3, the input plaintext is state 3. And in using mapping 3, state 3 moves to state 2. Let's draw that. So we're assuming using mapping 3. As an example, if my input plaintext is 1, 0, then one way we can think of that is that if this is 0, 1, 2, 3, we have input state 2. 1, 0 actually moves to position 1. That is, the input bits 1, 0 is this position 2 here, and on the output it's position 1. That's a way to think of the encryptor. It takes the input bits, which indicates a particular state, and the cipher simply rearranges those such that this 1, 0 comes out here. And that's what this diagram tries to illustrate, but with a 4-bit example. With 4 bits, instead of 4 values here, there will be 16 values here, 0 through to 15. So we take 4 bits input, gives us states 0 to 15, and the particular cipher, let's say C3, is illustrated here, where state 0, if I can follow that line, moves to state 14 in this example. So one way we can implement, in theory, this encryption block cipher is to map to particular states and simply This tells us to move anything that comes into state 0 to state 14 and so on. Which is really just another way to show this information. That is this column here. If I wanted to use C2, then this would be a different arrangement. Now, going back. So, that's the view of an ideal block cipher. It works. That is, all we do is we choose, or we allow any possible reversible mapping. We choose the one that we're going to use, and we select a key which indicates the specific mapping that we're going to use, where the key indicates the ciphertext bits. The key in general has a length n times 2 to the power of n bits. That becomes important in a moment. This shows what we've drawn on the board really, except for a different example where we have 4 bits input. This is one specific output. Here we have 24 possible outputs. With a 4-bit input, how many possible keys or how many possible ciphertexts are there? With a 4-bit input, I asked this question yesterday to the same area, how many possible keys are there? No thanks. I'm trying to talk. I cannot eat at the same time. With a 4-bit input, how many possible transformations or keys, it's the same value, are there? 2 to the power of 4, no. 2 to the power of 4 factorial with a 4-bit input. With our 2-bit input, there were 2 to the power of 2 factorial. With a 4-bit input, there will be 2 to the power of 4 or 16 factorial. Here is just one of them, just for the example. So we can implement a block cipher like this. What's the problem with it? The problem is that if we have a block size, n, which is large, our key becomes too long. Let's say n is 2, then our key is 8 bits. That's fine. I can send you a key of 8 bits, no problems. If n is 64 bits, then the key length becomes 64 times 2 to the power of 64. What's 2 to the power of 64? I need a calculator. Two to the power of 64 is 10 to the power of 19 bits times by 64, which is about 10 to the power of 20. So that's bits divided by 8 to convert to bytes, divided by, I think, gigabytes. That's the number of terabytes our key is. It's too big. If we have a 64-bit block, using this approach, our key needs to be something like 2 million terabytes. And I need to send you this key before we even communicate. I cannot write it on a piece of paper. I cannot send it as a file. It's too large. So if n is large, the key is too large to use this approach. Let's make n smaller. What's the problem? The problem of having n small is that so we have small block size, that the frequency analysis is possible. With a small block size, we'll get many repetitions. Let's see if we can illustrate that. The larger the block size, the less likely, the less repetitions we're going to have. Let's say this is our plain text. I'm just making up some bits. some random bits. That's our plain text that we want to encrypt. If we have a block size of 2 bits, then this is a block, this is a block. Every 2 bits makes up a block, and so on, and maybe more. So we have our plain text. That's a large file we want to send. We convert it to binary. If our block size is 2 bits, then it's likely that we're going to have many repetitions of those blocks. We can see repetition here. That is 0, 1, 0, 1, 0, 1, all right, 0, 1 here. Just in that small sequence of bits, there's repetitions already. If there's repetitions or patterns in the input plain text, then that makes it possible to do, potentially to do frequency analysis. If we have a larger block, 4 bits, for example, if we have a 4-bit block, does this sequence 0, 1, 0, 1 repeat? Let's look, 0, 1, 0, 1. It doesn't repeat here. It's not here. It's not here. It's not here. That block did not repeat in our plain text. It's less likely to have repetitions as we have a larger block. So therefore, a larger block is better from the point of view that there's less repetitions and therefore less chance to do frequency analysis. So we want a large block to avoid the possibility to do frequency analysis, so they cannot break the cipher. But we want a small block for the key to work. It turns out that the recommended values of the blocks are, well, larger than 30 or 40 bits, so 64 bits is typical for the block size. But 64 bits is too big for the key size. So in fact, we do not use this ideal block cipher as an approach to do encryption, because we're forced to use a small block, otherwise the key will be too large. But if we use a small block, we can do frequency analysis because we get more repetitions of the equal plain text. And that has led to the development of the Feistel structure. Mr. Feistel come up or worked this out and come up with a structure that instead of doing this direct encryption of taking some plain text and mapping directly to ciphertext, then simplified the encryption step, this mapping, make it smaller so we have a manageable key size, but do repetitions, apply it multiple times, and apply it in some structured manner. And that's what he came up with, the structure of applying substitutions multiple times combined with transpositions or permutations. So the idea is to apply 2 or more simple ciphers in a sequence so that the final result is still cryptographically strong, it's still secure, as opposed to what we just went through is just one encryption, one cipher, a complex cipher, but it's not practical. So let's look at this structure. We have an n-bit block length, so the block size is n bits, but we have a key length of k bits. With an ideal cipher, it was n times 2 to the power of n bits, but in this case, we specify the key to be short to make it manageable, k bits in length. As a result, with a k-bit key, we have 2 to the power of k transformations. So if we have a 4-bit key, there are 16 possible keys and therefore 16 possible transformations. The same here, we had 24 possible transformations, which meant we have 24 possible keys. The number of keys determines the number of transformations, and vice versa. And what the Feistel structure does is it alternates between substitutions and transpositions. Substitutions is we replace one element with another. Transpositions is we rearrange the elements. And it does it in a specific way. We'll come back to that. It's not so easy to see up here, but the general approach is that we have some input plain text of n bits, we separate it into two halves, the left and the right half. That's shown here. The input plaintext, we say that we have the left bits and the right bits. We take the rightmost bits and we apply some function on that using a key. And we'll come back to that, but it's a round key. Not a round key, but a key that we're going to use in a specific round of the operation. We apply some function, and the function has to be specified later, but we apply some function which is really some substitution. On the rightmost bits, we take the output of that function and exclusive OR with the leftmost bits and take the output of that, and that becomes the rightmost bits, and we take the original rightmost bits and send them to become the new leftmost bits. Then we do it all again. Take the leftmost bits, the rightmost bits, apply some function, XOR, swap them, do it all again. This is called a round, and we can have multiple rounds. Here it shows 16, which is common, but it can be more or less than 16. So this is the general structure of the general Feistel structure for ciphers. It's used by many ciphers. It's used by Des that we're about to go through, plus other ciphers. So it's used in ciphers in practice today. Not all, but many. So some of the concepts that we use in the Feistel structure is that we use some function which will contain at least a substitution. It takes as an input some part of the key or some operation of the original key. Here we see we have a key, key1, K1, used in the first round, a different key, K2, used in the second round. We have one key for each round. In fact, what happens is that the user chooses a key, just one key, and from that, the cipher generates round keys. In this example, it would generate 16 different round keys, one for each round. So there's an algorithm to generate the round keys. We use an XOR here, and we shift or swap the halves on occasions. We'll see the details of those operations when we go through a specific example of Des. What have we missed? Confusion and diffusion. Feistel developed this structure when he was, and actually Feistel developed a cipher called Lucifer with IBM, and Lucifer went on to become Des. Des was the main used cipher, and probably still is the main. It's not used now, but over all the ciphers used in the past, it's the most popular one. Feistel come up with this structure of alternating substitutions and transpositions. It applies the concepts of diffusion and confusion. So let's explain what they are. And these two concepts were developed or defined by Shannon. Everyone remember Shannon? Shannon capacity. Yeah. Nyquist and Shannon capacity. Claude Shannon come up with this capacity of data communications, how much data we can send across a communication channel. He also did a lot in cryptography. He come up with diffusion and confusion and several things regarding cryptography. So he was considered very smart because he come up with things in communications and cryptography and also in digital circuits. What is diffusion and confusion? In a very simple terms, I think. This is what we want to achieve with a cipher. We want to diffuse the plain text. Diffusion is about, we want to reduce the statistical nature of the plain text when we get the resulting cipher text. Remember, our plain text has structure. If we look at English plain text, that structure is the frequency of letters, it's the frequency of diagrams, trigrams, and the occurrence of words. So there's some structure in the plain text, in any plain text. Diffusion is that we want to reduce that structure in the output ciphertext. There are some statistics about the plain text. We don't want those statistics present in the ciphertext. That's the idea, reasonably simple. reduce the statistical nature of the plaintext when we create the ciphertext. Ideally, the ciphertext should look random. There are no statistical characteristics of the elements in the ciphertext. How do we do that? So that's the goal, well, that's what diffusion is, to diffuse the statistics across, or spread out the statistics in the ciphertext. The idea is that if we have an input plaintext letter or element, whether it's a bit or it's a letter from the alphabet, whatever, an input plaintext letter should have an impact upon many output ciphertext letters. Or the other way around, that a output ciphertext letter is impacted by many input plaintext letters. So that we'll see there's a measure for this, but if you change a particular, just one plaintext letter on the input, as a result, many ciphertext letters will change on the output. That's desirable. So if I had plaintext and I got some output ciphertext, from some encryption, and then I took some different plaintext, all I've done is change this letter from E to F. If I got this, then that's not so good, because in this case, changing one input plaintext only changed one output ciphertext. What would be good if I change just one input plaintext letter, I affect all output ciphertext letters. That's diffusion. The statistics have been spread out across the ciphertext. In fact, later we'll see that there's a way to measure that, to measure how much that impacts. One way to do that, and that's what the Feistel structure does, is to repeatedly apply permutations or transpositions. Remember, they're just rearrangements of letters, and apply some function on the output of those permutations. And that's where we'll see some function comes into the Feistel structure. What function, it needs to be defined. So there's some ways to provide diffusion, and Feistel structure applies those approaches so that the cipher is good from the perspective of diffusion. That's about the relationship between the plain text and the ciphertext. Another thing we care about is the key. We want to make the relationship between the ciphertext and the key as complex as possible, so that an attacker that has the ciphertext cannot find the key. Similarly here, this is saying if the attacker has the ciphertext, it's hard to get the plain text. Here we want to also make it hard to get the key from the ciphertext. So even if there are some statistical characteristics of the ciphertext, by having the relationship between the ciphertext and key very complex, it should be hard to go backwards. You've got the ciphertext, work back and find out what the key is. That's the idea here of confusion. To confuse the attacker, or to differentiate the ciphertext and the key. The way the Feistel structure does this, or the general way to do this, is to use a substitution algorithm which is complex. Remember substitution, we take one element, replace with another element from the alphabet. We'll make that operation a very complex operation. And normally make it non-linear. Non-linear means that, well, it's hard to go backwards.
Exponential.
Yeah. We'll see examples of that after we analyse DES, DES. So the Feistel structure applies these concepts of spreading out the plain text in the ciphertext, diffusion, and making the relationship between the ciphertext and key complex, confusion. The structure is applied in many ciphers today. The approach is listed here, it's in the diagram. Split the plain text into halves. Have round keys or sub-keys generated from like the primary key. You need some round function applied on the right half. Substitute and use it using an XOR, exclusive OR, and apply some permutation that is rearranged, swap the halves. But we'll see that in more detail in a moment. It's best to explain the general structure of the general Feistel structure using a specific example or a concrete example, Des. One of the advantages of this structure is that decryption, that is this side, is almost the same as encryption. And that is, when you encrypt, you take the halves, apply some function on the right half with some key, XOR, and then swap the halves and do it again. With decryption, you take the halves, apply some function, XOR, swap, and do it again. In fact, decryption can be the exact same steps as encryption, except use the keys in the opposite order, the round keys. The benefit here is implementation. I can implement the encryptor and use it as a decryptor as well. So I cut in half the complexity or the size of the implementation. So that's one of the benefits of this structure. That's talking about the general concepts. Let's go through an example that illustrates them. So some of the details. How large should the block be? Typical values are 64 or 128 bits. How large should the key be? Well, that depends upon, we want to be large enough to prevent a brute force attack. Larger values lead to more confusion. Similar larger block sizes can lead potentially to more diffusion. How many rounds should we have? We'll see some ciphers have 16 rounds. There's no exact best number. You want more rounds to provide more security, but less rounds to be faster in encrypting. How do we generate the subkeys? Well, we need an algorithm that should be complex. What is this round function f? Again, it should be complex. And there are other factors that impact on how fast an implementation is. And an important trade-off that we're going to mention, in fact, for the rest of the course, and that we see here, is security versus performance. Larger block will lead to more security. Larger key will lead to more security. More rounds will lead to more security in general. But all of them will reduce the performance. That is, it will take longer to encrypt a piece of plaintext. And that impacts upon the practical use of the cipher. So you need to trade off security versus performance in many cases. Feistel example we won't go through. Let's move on to a real cipher, Des, the data encryption standard. But before we move on, two things from yesterday. What was the first thing? The first thing was one-time pad. Someone yesterday pointed out an error in the one-time pad. Let's have a look. Let me find it. Let's see if I... What's the error? No, there's a problem. There's some mistakes here. What is it?
The mistake here?
Yeah. Someone pointed out to me yesterday. I can't remember. Maybe. Okay. I can't remember. No. What's the error? No, I don't think. Someone else. What's the error here? M. Yeah, you pointed it out yesterday. Well done. I think. M. This was the example ciphertext. This was, if we take this plain text, use this key, we're supposed to get this ciphertext. And if we take this plain text, get this key, we're supposed to get the same ciphertext. Doesn't quite work because you see, it may be hard, but the fourth character here is M. Encrypt M with key M and get Y as an output. But here, encrypt plaintext M with key M, but it says we get A as an output. That's not possible. With the Vigenère cipher, if we have the same plaintext input and the same key value, we'll always get the same ciphertext output. There's an error in, I can't remember which one, the second one, I think. I think the first, I've checked only the first 4 characters, not all of them. That's your homework. This one is wrong. That is, the key value is wrong. This should not be an M. And I think the third one is wrong as well. It's very easy to check because take M, take the value, and plus the value of this, and you should get A, which is 0, for it to work. If you take M and P, you should get A, which is 0. So whatever value of the key plus M gives A is the correct key value. And I think the third character is wrong as well. I don't know if any of the others are. This is I copied this from the textbook. The textbook's wrong. I should not copy. I should make my own. So just be aware that there is an error there. I will report the typo to the author. Maybe. Let's see. I've got 2 copies already. That's one thing. And about the textbook, someone asked the first week, is there one online? Is the textbook online or an e-book? Well, that exact one isn't, but there's another one online that is free. From the lecture notes. No, not from the lecture notes, sorry. Sorry. The resources, or a study guide, I think. Somewhere I have on this study guide page, I have a list of textbooks. The one online that's free is the Handbook of Applied Cryptography, this one. If you go here, you can download the PDFs of all the chapters. Now, it's a large one, it's a handbook, so it's probably 1,000 pages or more, but, and it's in some cases quite theoretical. But the first 2 chapters, and I haven't read them all, but I've looked at the first 2 chapters, and it is quite a clear explanation of the basic concepts of encryption and some of the things that we cover throughout this course. So it doesn't cover everything in the same order that we cover, but if you want something free and online, then it has a couple of chapters that are relevant. Have a look. Now let's go back to our lecture. Des. Des is a block cipher. Maybe one more thing. We've said block ciphers. We've also said stream ciphers. So we said with a block cipher, we want to make the block large so that frequency analysis is not possible. A block of 2 doesn't work with a block cipher. A block of 64 is typical and it works okay. Too small, frequency analysis is possible. Stream ciphers are built differently such that that problem doesn't occur. A stream cipher effectively works on a block of 1 bit or 8 bits. But the way they're implemented, that's frequency analysis is not possible. It's not possible because they use an XOR.
We need some commercial software or free software, but cannot implement by ourselves.
You can implement this by yourself. If the algorithm is known, you can implement it. Yeah.
Not harder than do myself.
I think you could implement all the ciphers we talk about in this course as an assignment quite easily. It may not perform well, but it'd be okay. It'd work. Des is a symmetric block cipher. What do I mean by symmetric? When I say Des is a symmetric block cipher, what do I mean by symmetric? Symmetry, but in terms of ciphers, what do I mean specifically? What's symmetric? Keys. That is, the encryptor uses a key to encrypt, the decryptor uses the same key, a symmetric block cipher. We're all the ciphers so far are symmetric block ciphers. Symmetric block ciphers. It uses a 56-bit key. In fact, the key is 64 bits, but 8 of those bits are used as a parity check. They're not used in the encryption phase. So effectively, it's a 56-bit key, 64-bit input, 64-bit output. We have n equals to 64 bits is the block size. It's one of the most used in the world. It wouldn't be used in new applications today, but in the past it's been used a lot. It became a standard, well, it was developed in 1977 by the National Institute of Standards and Technology in the US, actually come from the design by IBM of Lucifer with input from the NSA, and principles have been used in other ciphers. So even though Des as itself is not recommended, there's triple Des, which is directly based upon Des. And IDEA used similar principles. So it's important. But it's too complex for us to go through examples on the board. I cannot write down 64 bits and rearrange them. So some people have developed what's called Simplified Des, just for lectures, just for education. We will go through that on the board using examples so we can see the operations take place. It uses the same principles as Des, but everything's smaller. That's the difference. And therefore, it's easier to do in examples. It's not used in real life, Simplified Des, only used in this class. So know the difference. So let's go through Simplified Des, and once we've gone through that, we'll then explain how that connects to the real Des and some of the design issues with the real Des. Simplified Data Encryption Standard. We no longer have 64-bit input block. We're going to make everything smaller, and we're going to have an input block of 8 bits, and an output block of 8 bits, and a key size of 10 bits. Des, turns out, has 16 rounds. We repeat some process 16 times. Simplified Des has just 2 rounds, so we can do it quickly on the board. What we do is we start with a 10-bit key. For each of those 2 rounds, we need a sub-key or a round key. We generate those sub-keys from the original 10-bit key using some algorithm, and that algorithm is just made up of permutations, rearrangements, and a left shift. Shift the bits left. The encryption with Simplified Des, we take our input plaintext, we apply some permutation on the bits, we rearrange the bits, the 8 bits, we apply some function, which include a complex substitution function, swap the halves, and do it again in another round. And decryption is in fact the same as encryption, exactly the same steps, but we use the two round keys in the opposite order. That is, we start with a 10-bit key. We're going to generate two round keys. When we encrypt, we'll use round key 1, round key 2. When we decrypt, we'll use round key 2, then round key 1. And that's the only difference between encryption and decryption, the way that round keys are used. And those steps are summarised in this algorithm here. Encryption steps, decryption steps, round key generation steps. Let's focus on encryption. I start with 8 bits of plain text. All right, before encryption we need to generate our key. So the first thing, in fact, I start with a 10-bit key. I choose a key, it's a secret key. P means permutation here. P means we're going to apply some rearrangement of the bits. P10 means there's a specific arrangement of 10 bits. So the way that we read the diagram, 10 bits come in, we rearrange 10 bits in some specific order. A shift, in our case, is going to be a left shift on those bits. We take the bits, the 10 bits, shift them all left, and of course, one bit will wrap around and become moved to the end. P8, we see the shape of the box. The P8 here takes 10 bits as input. We have 10-bit key, apply a permutation, have 10 bits out, do a shift, we have 10 bits out. We're going to take some input and produce 8 bits out. And those 8 bits are going to be K1, or the first round key. And we're going to take some other the bits from the shift, do another shift, P8, and get round key 2. We're going to go through this in an example to show all these specific operations, just a summary at the moment. So we need to generate the two round keys using these steps, K1 and K2. Then to encrypt, we're going to take our plain text, apply some initial permutation, IP is the initial permutation only at the start of the encryption, rearrange the bits, apply some function, F, with the key as the input, switch or swap the halves. Remember back to the Feistel structure, we had the left half and the right half. In between rounds, we swap them. That's what we'll do here. Apply the same function again, but using key K2 as an input. Apply some permutation, which is the initial permutation, but an inverse of it. That's IP to the power of -1. And we'll get our cipher text. Let's do it with an example. This is some information we'll need, but let's go through the example to generate these keys. Let's see, is the example on the slides? Yes, this example. Stay awake. We need to get through this example today, and maybe even finish on Simplified Des and Des. I know it's hard work, but we need to push on through. So we're going to go through this example on the board using those values, but I'm going to flick through the slides just to illustrate the algorithm as we go. So this is the overview, encryption, key generation, decryption. What do these blocks actually do? Well, that's specified here. I'll explain them when we apply them. So that the operations, those blocks are specified or explained here. The key generation in more detail is explained by this diagram. Let's generate our key. We have a 10-bit key as input. So this diagram shows the details where we have 10 bits as input. We're going to apply some permutation on those 10 bits, rearrange them, and we'll get 10 bits as output, and we'll treat the halves separately. The 5 bits on the left and the rightmost half will be treated separately. So first let's apply this permutation. The permutation is fixed. It's defined for the algorithm. It's known. Whenever we apply this permutation, it's always the same. It doesn't change. What is it? It's defined P10 here. We have 10 bits as input. If we number those bits, we have bit 1 through to bit 10. We rearrange them so that they come out like this, that the third bit on input becomes the first bit on output. The 10th bit, the last bit on input, comes out as the 6th bit on output. The first bit, which is input to this operation, comes out as the 7th bit, and so on. That's fixed for simplified Des. It doesn't change. And similar in real Des, there's a similar permutation. It's larger because we operate on more bits, but does the same thing. So what we do is we take these 10 bits and rearrange them according to this permutation, and we'll get the output of the first step. And rearrangement, the third bit becomes the first bit. That is, this 1 becomes the first bit. The 5th bit, bit 5, becomes the second bit. 0. The second bit becomes the third. Bit 7. 4. 10. 1. 9, 8, and 6. This is the output from applying P10, permutation 10. Input 10 bits, output 10 bits. If I make a mistake as I go, someone will let me know. Any problems so far?
Teacher,
Yep.
so are we using the computer to do this, or are we?
Oh, I'm using my head.
My head.
Very easy. Rearrange bits. Of course, you could be asked to implement it on a computer for sure. And it's quite easy to implement. But no, in an exam, you would use your head. Any other questions? Everyone understands the idea of a permutation? It's fixed. P10 is always this permutation. We'll see there are other permutations listed. P8, P4. We'll use them shortly. Next step. Now let's go back or forward. That was this step, P10. We treat the two bits, the two halves separately. Now we have two sequences of 5 bits in length. LS1 is a left shift. LS, left shift by 1 position. Take these 5 bits and apply a left shift, which means this bit wraps around to the end. This bit moves to the left. This bit moves to the left by one position, one position, one position. So it becomes... Okay. Just shift them all left, but of course the leftmost bit becomes the rightmost bit. We only do it on the 5 bits, not on all 10 bits. That is, we treat the left half and the right half differently, or separately. So we do the same on the right half. A left shift by one position. The second bit becomes the first bit. And we get these 10 bits as an output. Or two halves, the left half and the right half. We input those 10 bits into permutation P8. P8 takes 10 bits as input and produces 8 bits as output. So it's in fact select and permutate. Select and rearrange bits. We discard 2 bits. Any questions on the left shift? L means left, S means shift.
Left shift 1.
1 means one position. We may see later, or in other algorithms, there's a left shift. LS2 means shift by 2 positions to the left.
It's like rotate.
Like rotate, yeah. Shift to the left. If we think in binary, we often do a shift in a register and so on. In digital circuits, and hence it's easy to implement. And implement in hardware as well. P8, take 10 bits as input, these 10 bits, and select and rearrange P8. Six, 3, 7, 4, 8, 5, 10, 9. 1, 2, 6, 7, 8, 9, 10. We just take 8 of those bits and rearrange them such that the 6th bit, 6, 3, 7, 4, 8, 5, 8 is 0, 5 is 1, 10 and 9. 10 is 0, 9 is 0. We discarded bits 1 and 2. We didn't use bits 1 and 2 in that operation. The first 2 bits. Y comes later. Let's just go through the algorithm. We'll see when we look at the design of Des some of the reasons for some of these operations. But remember, from our general Feistel structure, the idea is to have substitutions and transpositions alternating between substitution, transposition, and repeat and repeat and repeat. Transposition is permutation. These P's are transpositions. They're rearranging bits. The substitution we'll see later. P8. And we have key 1 now. Where's my pointer? That was this operation. The output is key K1, or round key K1. K1 equals this value, 1, 0, 1, 0, 0, 1, 0, 0. We're going to use that in the encryption and in the decryption. Let's move along. We need to generate round key K2 as well. We need 2 round keys because we have 2 rounds. We take what we had before the P8, do a left shift by 2 positions on each of the halves. That is, we take this, I'll write it up here, That is, we take the 5 bits and the 5 bits, and on each 5 bits we do a left shift by 2 positions. A left shift by 2 positions means this one will not move to here, it will move to the 3rd bit. Everything's rotated or shifted to the left by 2 spots. And the same on this side. Thank you. That is this step. Well, those 2 steps there. And P8 again, the same P8 as we did before. Select and permutate. 6, 3, 7, 4. We take bit 6, 3, 7, and 4, which is 0, 1, 0, 0. 8, 5, 10, and 9. 8 is 0, 5 is 0, 10 is 1, and 9 is 1. That's key K2. Zero, 1, 0, 0. 0, 0, 1, 1. That is the key generation algorithm for Simplified Des. I think I'm going to stay over this side, which is this process we've just done. Both the person who wants to encrypt the plain text and who wants to decrypt the ciphertext must do this exact same algorithm. I have some plain text, I choose a 10-bit key, I generate K1 and K2, I send you some ciphertext after encrypting. You must know my 10-bit key, it's a shared secret between the 2 of us. You generate the same values of K1 and K2. You apply the same input key, you use the same algorithm, therefore you'll get the same output K1 and K2. Any questions on key generation before I remove it from the board? We haven't decrypted yet. The goal here, and we only do it for Des, we don't do this detail in other real ciphers. We do it here just to illustrate some of the operations, not for you to remember the details of how Simplified Des work, but just to illustrate different operations on the binary values. And then we'll explain their significance. We have generated the 2 round keys. We now want to encrypt our plain text. What's our plain text? Is that the plain text from the slide? Is that the plain text from the lecture notes? Check the slide. Next one, next page. Okay, this is the plain text that's on slide 24 on your lecture notes, and we've generated the round keys. We need to do some permutation on that, IP, not the Internet Protocol. We're going to apply some function, which we need to define shortly, swap the halves, apply the same function, and do an inverse of that initial permutation. Those steps are defined. Oh, here's initial permutation. It's just another rearrangement of 8 bits. Here is the details of the encryption. 8-bit input, initial permutation, This is the function. The darker grey box is f of k. Let's look at what happens here. After the initial permutation, we have 8 bits. We treat the two halves separately, the left half and the right half. The rightmost 4 bits we input into this procedure. EP means expand and permutate. We take 4 bits in, the right 4 bits, expand and rearrange. That is, with 4 bits in, expand, basically copy those bits so we get 8 bits and rearrange in some way. That rearrangement is defined here. 4 bits in, 8 bits out. That's this step, expand and permutate. 8 bits out. Then we'll do an exclusive OR with the round key K1. K1, which is over here, exclusive OR with these 8 bits. Then we'll take the 2 halves again, split it into 4 bits in each half, and apply a substitution. There's 2 substitution functions here, S0 and S1, and these are called S boxes. The P's are called P boxes, permutation boxes. The substitutions are called substitution boxes or S boxes. S box 0, S box 1. So we'll show you what that substitution is in a moment. That's the complex substitution algorithm that we need for the security. And in fact, for the confusion to arise, we need an S box. We're going to take the output 2 bits of those S box, do another permutation, XOR with the left half. Then we have 4 bits, we have the right half, and then swap the 2 halves. The left becomes the right becomes the left. And then we'll do the same. It's exactly the same as here, except we'll use key K2 instead of K1. When we're finished, we'll get 8 bits out. We'll do an inverse of the initial permutation, and we get our ciphertext. Easy?
No.
Why? What's hard? Remember, we have permutations and substitutions. They're the main operations. Permutations are transpositions. When we looked at the rail fence cipher, the rows column cipher, they were rearranging letters, permutating. This cipher is a combination of permutation, XOR, substitutions, permutations, a swap, rearrange, it's just a permutation, and repeat again. So it's just multiple operations of permutate, substitute. Yes, we're going to have an example, and we've got 20 minutes to finish it. So let's see how fast we can go. Initial permutation. So any questions before we go through this quickly? Permutate. So we have IP, initial permutation, expand and permutate, P4. They are all here. P4, IP, expand, permutate, same as before.
Can we apply this to input like 10 bit?
Only 8 bits plain text. If you have plain text of 16 bits, you need to do this twice on each 8-bit block. Let's go. Initial permutation. IP. This is the rearrangement. Let's get a different pen. IP bits 2, 6, 3, 1, 2, 6, 3, 1, 4857. 4857. That's the result from the initial permutation. We now separate it into two halves and focus on the right half here. The output of the initial permutation, we have 4 bits on the right, 4 bits on the left. The 4 bits on the right are fed into the expand and permutate, EP. Don't worry, we'll get to a fun bit in a moment. Take the right half, expand and permutate, which is simply defined here. Bit 4, 4, 1, 2, 3, 4, 1, 2, 3, and then 2, 3, 4, 1. 2, 3, 4, 1. I just did this operation. Bits 1, 2, 3, 4 come in. The outputs are bits 4, 1, 2, 3, 2, 3, 4, 1. We've expanded to 8 bits now. Here. On the rightmost 4 bits, yes. That was this step. Output of the initial permutation, we separate into 2 halves. Yeah. Rightmost EP. Yep. No, we haven't rearranged. Oh, we've done input plaintext, 8 bits, initial permutation, rearrange there. And then take the right bits and expand and permutate. Next step, XOR with a key K1. K1. I'm going to take these 8 bits, exclusive OR, with K1, which we generated before. One, exclusive OR 1. Wake up. 0. 1, 0, 1. Just exclusive OR those two values. Now take, again, separate it into 2 halves, and I'll write them up here. Let's deal with the left half first, the first 4 bits. Left half is 0, 1, 1, 0. 0, 1, 1, 0. Feed these left 4 bits into S box S0. This is the fun part, or the different part from before. S box S0 is going to do a substitution. Take 4 bits in and produce 2 bits out. Any questions before we go through the S box? We're about to do S0 right now. I cannot repeat because I haven't said it the first time. Any other questions? Let's go through an S box. The S boxes are defined here, S0 and S1. Let's explain how they are used. This is the substitution operation. So far we've just done rearrangements. Here we need to take some input elements and replace with others. Not rearrange, but substitute. SDES, as well as real DES, do the substitutions using substitution boxes, S boxes. Other ciphers use S boxes as well. We read it as a matrix. The input to the S box is used to select the row and column, and the selected element is the output. So we have a 4 by 4 matrix, 4 rows, 4 columns. And be careful here. We number the rows and columns starting from 0. Row 0, 1, 2, 3. Column 0, 1, 2, 3. That's the way to think of that matrix. We start at 0 with the numbering here. So we have 4 bits input. Bits 1, 2, 3 and 4. What we do is we take bit 1 and bit 4 to indicate the row. Which is 0, 0 in our example. These 4 bits were the leftmost bits of the output of the XOR. So if you, that is here. We did the exclusive OR, we take the leftmost bits and they're the input to S0. So I've just got these 4 bits at the moment. Bit 1 and 4 will tell us the row of the matrix, and bits 2 and 3 will tell us the column. One. And simply we look up the matrix. We look at row 0, or 0, 0 in binary, decimal 0, and column 3 in S box S0 we're using here. This is fixed. Same as the permutation, this S box is defined. It's always the same. It doesn't change for simplified Des. We always use this S box where we see S0. Row 0, remember 0, 1, 2, 3. Row 0, column 3 here. Column 0, 1, 2, 3. The output of the bits 1, 0. If this is the input to S0, the output is this element here. Row 0, column 3. That's how we use the S boxes. We use the input to look up the element based on the row and the column. If you understand that, you can easily get the output of S box S1. We do the same. We just did it on the leftmost bits here, the left 4 bits. We do the same for the right 4 bits using S box S1. 0, 1, 1 is the input. What's the output? Try it. Try it now. Try it and write it down. Okay. What's the answer? S1. The output is 1, 1. Row 0, 1, column 1, 1. Row 0, 1, column 1, 1. Remember, you start row 0, or in binary, 0, 0, 0, 1, 1, 0, 1, 1. You can think of the rows and columns in binary or decimal. Row 0, 1, column 1, 1, output is 1, 1. So we now have 4 bits. 1, 0, 1, 1. On those 4 bits, apply P4. We have 4 bits, the combination of those 2-bit output, two 2-bit outputs. Apply P4. 1, 2, 3, 4 becomes 2, 4, 3, 1. 1, 2, 3, 4, 2. That'll be the output of P4. I hope.
S0 is 1, 2, and S1 is P4.
Yes. Make sure you need to follow these diagrams as well. That is, if we have 2 bits output, it says how many bits are output here. We got 2 bits. Essentially we join them together to get 4 bits here, the left and the right 4 bits. We're here. We took the outputs of the 2 S boxes. We had 4 bits, 1, 0, 1, 1. We rearranged according to P4. We get 4 bits. Now we exclusive OR these 4 bits with the original left half from the initial permutation. Here, after the initial permutation, we said right and left halves. We take this and exclusive OR with this. The output from P4, which is 0, 1, 1, 1, the left half of the output from an initial permutation, the left half from here, 1, 0, 1, 0. Exclusive OR those.
1, 1, 0, 1.
Gives us 4 bits. Now, take the right half of the initial permutation. We used it before, but we'll use it again. 1, 0, 0, 1. So this is the right half. The right bits from the initial permutation, which was 1, 0, 0, 1. So we're here now. That's the output of the function fk, those 8 bits, 1, 1, 0, 1, 1, 0, 0, 1. The output of the first round. output of P4, 0, 1, 1, 1. Left half from IP.
And so is 1101 and then
1101. This is the right half of the output of the initial permutation. Original plain text, initial permutation, the right half. 1001. Yes. So we have 8 bits. We're here. Swap the halves. Do it all again. Do the same steps, not the initial permutation, but the same steps inside the function again. Round 2. Expand. XOR with K2. Not K1, but this time K2. Almost done. Last thing, the output here, what did I get? The output there turns out to be 1110, 1101. That is f of k. This dark grey box, this is the output. The last thing is we do an inverse permutation. Find the inverse permutation, or the inverse of the initial permutation. Find the inverse of the initial permutation, apply it on those 8 bits, and you have your ciphertext. And in your lecture notes you have the answer ciphertext. Work out what IP, the inverse of IP is. There's your homework for tomorrow, or for one piece of homework. And that finishes for today.